Okay, I'm going to call this either Chapter 5 homework hints or just kind of a way to look at some of the big concepts that we had in Chapter 5. Yeah, do it different than your homework. I can't remember which way your homework did it. Do it this way. Oh, actually, yeah, let's do it this way. Oh, let me actually look at my notes. I want the numbers to come out nicely. Interesting way to present it. Okay. What I want you to notice here is on the left side, the bottom is 2 times the top. Oh, whoops. The left side of the bottom is twice the left side of the top, but that's not the case for the right side. Okay, so we know there's no solution. And then what we saw in Chapter 5 is some non-solutions are better than others, and we talked about how to find the best one. So I want to put some of the pieces together. In the matrix form, we had another way to represent a system of equations. And with this perspective, since our matrix is transforming input vectors to output vectors. Okay, so when I look at this matrix, for the first column, the y coordinate is 2 times the x column. For the first column, y coordinate is 2 times the x coordinate. And that's the same for the second column. So remember, what we do to compute an output is take a linear combination of the columns. The input is the scalars that we use. So we see that the column space of the matrix is this line y equals 2x. So what that means, hopefully this just puts everything into perspective that we did last class or last chapter. So any input that I have here is going to get mapped somewhere to that line. So all of the outputs are mapped to somewhere on this line. And sadly, five zero is over here outside of the column space. So one way of saying that this system doesn't have a solution is that the output we're trying to get is not in the column space of the matrix. Okay, so let's call this B. The best non-solution to AX equals B is the solution to AX equals this, where the B parallel is projection of B onto the column space of A. Okay, so that's the best that we can do. So let's find that projection. So I'm going to do this two different ways. So, actually, I'm not sure. Maybe. Yeah, this is ambiguous. So first, let's see. By hand, I'm going to find the projection of B onto the column space of A. So the column space of A is the line y equals 2x. And there's a lot of different, I think we've probably come up with 4 or 5 different ways to do this in class. I'll just do one. So there's a basis for the column space. And then Gram-Schmidt with one vector just normalizes it. So there's an orthonormal basis for the column space of A. So if we factored A into QR, our Q matrix is this. And the projection matrix is Q transpose. Which is 1/5, 2/5, 2/5, and 4/5. Okay. And then B perp, remember, B parallel, which is projection of the B onto column space of A. Oops, they don't have the square roots there. Yeah, just redraw the picture again. Input space, output space. The A matrix is the one that transforms inputs to outputs. The column space of A is the line y equals 2x. Here is the output we're trying to get, which is impossible. This is what we can't get. So back to our original system of equations. The best that we can do is solve this system instead. So back to chapter 1. Elementary row operations. Not surprisingly, it's this second equation has no new information. So got an unknown x and y. This tells me somehow how x and y are related to each other. The second equation doesn't tell me anything new. So the best non-solution satisfies x plus 3y as 1. Did we do this already? We did. Okay. Is it worth doing again? Yeah, sure.
The quadratic ones felt hard.
Got it. Okay.
It might have just been more scary.
Got it. We can talk about that. Oh yeah, we've done all of this, right? Okay. So I don't need to finish this up. For some reason I thought we didn't do it here. Oops. So I'll just briefly go over it to finish this up. Okay, and then the punchline was this line is parallel to the null space. Okay, then the best non-solution is perpendicular to the null space of A. In other words, it's in the orthogonal complement of the null space, which is the column space of A transpose. Oh, the best, okay. Yeah, okay, and then to be in A transpose, so column space of A transpose, A is the matrix 1, 2, 3, 6, A transpose. Oops. Yeah. I'm going to copy this down wrong. One columns there. Okay, so. So I'll leave it there. I did do this before. Do you want to talk about a quadratic one?
I mean, it should be pretty much the same, right? It
Right,
just-
yeah.
It just scared, I don't know, I just kept messing up for some reason.
Okay, actually, let's talk about it.
So I'm gonna go over here. So I open that.
So this is what you're referring to?
I think so.
This is the Fourier one. It's gotta be that. Grab some stuff right here. Once. 0, 2, 4, 2, 3. Three, 1. Oh, this is touching. Great. Y is ax squared plus bx plus c. Our equations are 2 equals c, 4 equals a plus b plus c. So far, so good. Then I would use Sage Math here. I agree. It's the computations get a little complicated. Maybe that was my problem.
So yeah, let's
I was
talk
trying
about.
to do it all by hand,
Oh,
so
got
that I could practice for the test.
Okay. Want to see it in Sage?
If you want to.
Yeah, let's go. So I'm going to use this as my coefficient matrix, 0a plus 0b plus c. So 0, 0, 1. First row. Second. Or 2. Yeah, I'm like, don't like exams in general. Doesn't feel like it's really testing you. Here's my A. Shape first. Okay, so that's 2, 4, 3. Okay, then this way. Remember the steps. Like that.
AX equals B, but it has no solution. Multiply both sides by transpose. And there's our solution. Let's put that in. Transpose solution. Transpose times inverse transpose. Is that right? It's gotta be. Okay, so our X solution is -1/13/5. 1/10. I'm gonna go with decimals. C, so the best quadratic fit is -x² plus 2.6x plus 2. So I get why you're doing it for the test, just to make sure you can do the computations. Your sage math. So a little easier. I agree. New material. Yes. For some reason, I thought we hadn't covered the one I just did. Okay, my least favorite chapter. Let's see, let's back up for a minute. Okay, so remember in chapter 1, let's call this the chapter 6 overview. Yeah. Is we looked at the dot product as a perpendicular detector. Dot product is 0, the vectors are perpendicular. Dot product not 0, they're not perpendicular. And then we saw in chapter 5 that we can do a lot more with a dot product. Not just a perpendicular detector, but we can do projections, we can find the actual angle between the vectors. And then also in chapter 2, we said the shortcut rule for finding the inverse of a 2x2 matrix is like this. And sometimes this turned out to be 0. Should write it this way. So we can think about this expression as an inverse detector. So again, if the dot product is 0, the vectors are perpendicular to each other. If this number is 0, the matrix does not have an inverse. If this number is not 0, then it does have an inverse. So we have a name for this quantity called the determinant of A, B, C, D. And two things I want you to know. So one, determinant does a lot more than just detect inverses. And two, it's every square matrix has a determinant. Okay, so in this class, two things. So is how to calculate the determinant for any square matrix. I'm going to show you three different ways to do that. So if linear algebra is a prerequisite for another class that you're taking, they'll expect you to know how to calculate this determinant. And then two, what a determinant says about the matrix. Okay, no, different class. Okay, so just like we had the unit circle in trigonometry and the canonical L in chapter 2, I want to talk about, I'm going to call it the unit square. I don't know if it's really the right name for it. And I want to emphasize that we're not just looking at the boundary, but the entire two-dimensional shape. And the unit square is defined by two vectors, 1, 0, and 0, 1. So the area of the unit square is 1. Okay, and then this comes over here. Oh, the unit square is defined by these two vectors. So 1, 0 gets mapped to where? You remember why 1, 0 was one of my favorite inputs? Because it's gonna, the output is gonna be the first column. So. Oh, that's fair.
And then similarly, that 0, 1 gets mapped to 1, 3. And while I'm at it, I'll just think of it as a point here, is 1, 1 gets mapped to 4, 4. So if I fill in the pieces, is this input unit square gets mapped to this parallelogram. Okay. And through some geometry that's a little bit too tedious, you can work it out on your own. I'm just going to tell you the punchline. Is this has an output of 8. So what I want you to notice is this transformation transforms its input shape. So I take an input shape and then it gets distorted, it gets converted into an output shape, and the area changes. Is this little unit square got mapped to a larger parallelogram, and the area, it got 8 times bigger. The area increased by a factor of 8. And if I do that AD minus BC, this way, is I get the number 8. So it's not a coincidence. So it's just to make things official. So the name, that number that we calculate for a given 2x2 matrix is called the determinant. We'll get some nice notation. So we think about this as a function whose input is a matrix and whose output is that number. And sometimes, just for notation purposes, we use absolute value with the 4 numbers and don't put any brackets around it. And that's how we calculate the determinant. So is what I call the area expansion factor. Okay, so we just saw the determinant of this is 8. So let me do another example. So here's the unit circle. So that's the one where the center is 0, 0, and the radius is 1.
And this is something that we'll talk about. So roughly, this will be a chapter 7 topic. So its output is an ellipse. And very roughly, the radius here is 1. It's the length of these two axes for the ellipse are 4 and 2. The area of the circle is pi. Area of a circle in general is pi r squared. R is 1 for the unit circle. So this area is pi. This ellipse, the major axis, has length 4, or I guess, and the minor axis has length 2. Area of an ellipse is pi times a times b. The area of this ellipse is 8 pi. And I already knew that was going to happen because the determinant of this matrix is the expansion factor. So this matrix will take an input shape and deform it into an output shape. The output shape will always have 8 times the area as the input shape. Okay. And then 3 dimensions, for a 3 by 3 matrix, the determinant is a volume expansion factor. Okay, so here the idea is a 3 by 3 matrix takes 3-dimensional inputs and produces 3-dimensional outputs. So if you take a 3-dimensional solid, calculate its volume, and then look at how that solid gets transformed, you got that output solid. It has a certain volume. The determinant tells you how much the volume expanded by. So we'll go back and forth. Let me just talk about the calculations. So I'm going to show you 3 different ways to calculate a determinant. The first is using the elementary row operations that we learned in chapter 1. The second is what's called the cofactor expansion. And the shortcut rule is only for 2 by 2 and 3 by 3 matrices. And you've got the 2 by 2 shortcut rule already. It's just AD minus BC. And I'm going to show you something called Serres's rule, which will show you a fast way to get the determinant of a 3 by 3 matrix. Okay, so let's talk about the elementary row operation. It's a way of finding a determinant. So Now let's lowercase Roman numeral these. Okay, so remember the three types of elementary row operations we had? Multiply a row by a non-zero constant, swap two rows, and replace a row by the sum of that row and a multiple of another row. Okay, so what I'm going to do is see how the determinant changes each time. Let's back up. So remember, this was the identity matrix. Where whatever input you give to this matrix, the output is the same. It just doesn't change its input. So if I have an input shape and apply this matrix to it, I get the same output shape. So what's the determinant? Determinant is how much the area expands by. So the new area is the same as the old area. In other words, the new area is 1 times the old area. Or if we want to use the AD minus BC, the determinant here is 1. Okay, so I'm going to take this matrix, replace row 1 by 3 times row 1. Okay, now watch how this matrix transforms. Well, because yeah, this is visually a little bit better. So if I have my unit square, oops, let me try to be consistent with the colors. So it's purple. And what did I do? Scroll, scroll, scroll. That was green and red. Okay, so what this matrix is doing is just stretching along the x-axis. So it made the base of the rectangle 3 times longer. Or from the AD minus BC calculation, is the determinant of the new matrix is 3. Okay, so if I replace row 1 by 3 times row 1, the new determinant is 3 times the old determinant. Okay, next one. If I swap 2 rows, oops, let's do it this way. This is a little bit weird. So the determinant is negative here. So I'm going to talk about what a negative determinant means. So that's just going to swap the rows. So it's the same shape, but notice as I go from x-axis to y-axis in the original, this is counter, so x to y. It's counterclockwise. And transformed x to transformed y is clockwise. In other words, so there was a reflection. So I shall write it this way. So if the determinant is negative, the interpretation is that there were an odd number. So A did an odd number of reflections. So if you swap two rows, the determinant changes sign. Okay, and as a warm up for the third one, actually, let's back up a little bit. Yeah, maybe that. I don't know how you want to look at it. Okay, so roughly a parallelogram is really two triangles. The area of a triangle is 1/2 times base times height. There's two triangles. Area of parallelogram is base times height. Okay, so I've got my 1, 0, 0, 1, where the determinant is 1. Let's see, I'm going to replace row 1 by, I think, 3 times. Oh, actually, I think you can see the picture. Also, two things. Just doing the shortcut calculation. The determinant here is 1 times 1 minus 0 times 1/2, which is still 1. Or if I draw the picture, it's this is still 1, 0, and this goes to 1/2 one, fill it in. So the height here is still 1. The base is 1. It just got tilted over or skewed by a little bit. Is the determinant didn't change. Okay, so just to recap, the 3 types of elementary row operations. So replace a row by a non-zero multiple of that row. The new determinant is k times the old determinant. Second type of elementary row operation, swapping 2 rows. New determinant is -1 times the old determinant. And the third one, which is, I'll just write it this way. Is the determinant doesn't change. Yes.
When you do the swap 2 rows.
Uh-huh.
The determinant was negative. So when you swap 2 rows, you have to multiply -1 with the determinant.
Right.
So let's say like you're in the process of making it to an identity, making the matrix to an identity matrix. You have to swap rows.
Right.
Yeah. Okay.
Yeah, and I'll do 2 examples to be clear from that. 2 more things. If I have a diagonal matrix, so hopefully you can see this. So if I start with a 1 by 1, this becomes length A, this becomes length B. The determinant is just the product of the diagonal entries. And for a 3 by 3, you should see it as well. So if I have a unit cube, if I have any shape, expand along one axis by 2, another axis by 3, and third axis by 4, the volume goes up 2 times 3 times 4. Okay, so for a diagonal matrix, determinant is the product of the diagonal entries. And the other observation is if I have an upper triangular matrix, so this can be row reduced to a diagonal matrix using only type 3 elementary row operations. So here, this is actually true for upper triangular. In chapter 1, we used elementary row operations until we got a matrix in reduced row echelon form. Here, when we're calculating determinants, we just have to get it to an upper triangular matrix. So I'm going to do 2 of these. What's that?
So just the, this sort of triangular is like the numbers are on the top and the zeros are on the bottom.
Yes. Okay, we already know the answer from the shortcut rule. In your head, what's it going to be? The AD minus BC. Yeah, 4 minus 6. So we know the answer is going to be -2. Let me show you how to get that with the elementary row operations. So I'm going to replace row 2 by -3 times row 1 plus row 2. And let's see, this is -2. Okay, this is upper triangular. So the determinant is 1 times -2, which is -2. This type of operation doesn't change the determinant. So the original determinant is -2 as well. It gets more interesting with the 3 by 3. So let me show you how that works. Okay, fairly carefully chosen matrix. Okay. So I swapped rows 1 and 2. And I'm going to keep track of the determinant change here. So the determinant when I do a row swap, the determinant gets multiplied by -1. Then we replace row 1 by half of row 1. Oops. How are we doing on time? Oh, we got 4 minutes. Okay. I'll finish this example. And the determinant gets multiplied by a half. Okay, so then I'll take this one. I'll replace row 2 by -4 times row 1 plus row 2. Row 3 gets replaced by -7 times row 1 plus row 3. So -4 is 0, -3, -6, 0, let's see what, -7, -14 is -6, and -11. Okay, almost upper triangular. Yeah, do it down here. Replace row 3. Oh. And this is the elementary row operation that doesn't change the determinant. And then finally, I replace row 3 by -2 times row 2 plus row 3. -2. And that's -1. Okay, now we can just calculate the determinant here. Easy to do in your head. It's upper triangular, so the determinant is the product of the diagonal entries, which is -3. Okay, I multiplied mystery number by 1 to get a determinant of -3. So that must mean that the determinant was -3 before I started. That means the determinant is -3 here. Okay. So to get a determinant of -3, I multiplied this determinant by 1/2. So what was the determinant before I multiplied by 1/2? So when I multiplied it by 1/2, I got -3. What was it before that? Right, the determinant was -6. And then finally, I multiplied the determinant by -1 and got a -6. So the original determinant must be 6.
For past tense, so can you say what would happen if it was lower triangle?
Same thing. Yeah, we're not going to talk about it, but one fact is the determinant of the transpose of a matrix is the same as the determinant of the original. And so transpose of upper triangular is lower triangular. So they'll be the same product of the diagonals. Okay, so I'll finish up determinants on Wednesday, and then we'll get into the, this is not interesting. We'll get into the interesting parts of this class. Linear algebra, morning class, there it goes. And while I'm at it, let's put this to the evening class as well. Okay, cool. Have a good day, everybody. That's it.